Okay, let's get started. Now, let's continue to talk about flaws and how the role of flaws play a part in fracture mechanics. Now, we talk about there are two issues with the classical string theory, right? First of all, there is a statistical effect. The piece of solid contains a lot of different flaws, and then the flaws have different strengths, and therefore you have a distribution or a statistical scatter of strength in materials, right? That's issue number one, which we will not deal with today. Then the issue number two is that if we compare the theoretical strength that we calculate based on atomistic calculation, atomic plane separation, that is going to be a few orders of magnitude higher than what we measure in the lab, right? So there is something that is not accurate in our calculation of the failure stress, right? When we are doing the classical strength theory. And we talked about the reason being that we have not taken into account the presence of flaws in the calculation of the critical stress inside the body, right? So the calculation with the atomic, separation, that is okay, right? That is okay calculation. Is the calculation or the error lies in we are not accounting the right stress inside the body because we don't have a flaw in the calculation. So to do that, that's what we're going to deal with today, right? We want to assume there's a flaw inside the body, right? There's a hole inside a piece of solid. And we want to use the theory of elasticity to calculate a more precise number or value of the stress around the flaw when we apply a certain amount of macroscopic stress, right? And see if that stress will help us get closer to that theoretical calculation. And basically, this is a problem in elasticity, right? Because we are calculating the stress field of a piece of solid with a certain amount of flaw or a hole inside that. And this is not an easy calculation, actually, right? Analytically and mathematically, this is quite difficult. And these days we can do it with numerical methods, but imagine the time of English, which is 1913. We didn't have finite element, right? So this is a question that he had to deal with for analytical solution. So let me quickly review what we mean by elasticity theory. I will not go through all of it. Just a refresh of your memory when we talk about this, and I'll just strictly jump into the result or right after we do this review. So I hope this will bring us all into the same page because we are not going to go through the details. I'll just immediately show you the results obtained from these previous work, and just to be sure we are on the same notations and you know what I'm talking about. We have this very quick. I'm going to list some of these equations that you should have known from intermediate of mechanics and materials, right? So if we think about a solid mechanics problem, a boundary value problem. So the governing equations, basically there are three components, right? We have the kinematics that deals with the displacement and strain, right? And then we have the equilibrium equations that deals with the relation between the applied forces with the internal stresses, right? So kinematics deals with just geometry change. Equilibrium deals entirely with forces and stress, and they are not related, right, yet. And that gives us the third component, which is the kinetics, which is another way of saying that what is the relation between stress and strain for a particular solid, right? Because that is different from material to material, and that is another word to say that is what is the relationship, what is the material property between stress and strain for a given material. Now this is something we obtain from experiments, right? Because we do an experiment, we obtain properties like elastic modulus and Poisson's ratio. Then this describes how the stress and strain are related. So in three-dimensional elasticity, we are looking for, in our governing equations, So if we have to look at the kinematics, basically that means strain displacement, displacement and strain relationships, right? So we have displacement fields, right? So I'm going to write down this. Just list these equations out, right? So we have displacement fields, and the purpose for us is to solve for three different displacement in three-dimensional space, obviously, right? And now they have to be functions of coordinates, right? They vary within the piece of solid, and that's what we mean by field. It's a field, a result of field equations. Better? Yeah, it was blurry. Okay, so kinematics that take care of the strain field with respect to displacements, right? So we have the strains. That's basically, we have 6 strains, right? So the normal strains deal with length changes, right? And we have the shear strain that deals with angle changes. And they're related by the partial derivative to the displacements, to free displacements. So you differentiate the free displacement by the free directions, then you get 6 components, and that's the strain components, right? So we have 6 strain components in 3D. Now, most of the time we deal with 2D in this class, but I'm just writing down this equation in general. Now let's go to the kinetics first, right? The kinetics, what we're going to deal with is just elastic materials. So we're dealing with linear elastic material for most part of the class. And for linear elastic material, we use Hooke's law, right? So we assume the material is isotropic, linear elastic, and for that material, we can describe the material properties by, basically 2 independent material properties, right? So I'm going to write it down in terms of the elastic modulus E and the Poisson's ratio. Obviously, you can change it to other set of constants. You can do shear and bulk, or you can use the Lamé constants. Doesn't matter which set you use, only 2 are independent. So these are the very base fundamental equations that you don't have to copy if you don't want to. These are very standard in many textbooks. I'm also going to upload my lecture notes as well. Okay, again, corresponding to the 6 strain components, we have 6 equations that relates the 6 strain components to the corresponding stress components. Now I'm having a sigma as my stress. Okay. Now, finally, we have, so this relates the kinematics relates the displacement to strain, and kinetics relates the strain to the stress. Now, we need a condition on the stress to now actually close the problem, right? Because we need the final part, which is equilibrium. basically is the Newton's second law, right? The momentum balance equation. Now we're dealing with only statics, right? So in this class, we are not dealing with dynamic problem. And most of the time, we are going to neglect body forces. Not most of the time, all the time in this class, right? So all the forces that we are counting are forces that apply on the surfaces of the solid. Gravitational forces we will neglect, so there's no body forces. And what I mean by dynamic, it means that all the problems and all the equations we write, they're not going to be dependent on time. Okay, stress and strains, they're not going to be dependent on time. Elastic material, the properties don't change with time. Okay, these are very classical problems that we deal with in elasticity. So the equilibrium equation then becomes quite simple. These are all component form. It boils down to all the derivative. So Bx is the body force, right, which we are going to neglect most of the time. It's going to be in equilibrium. So all the forces or the stresses inside a solid should become zero. There's no net forces. Again, there are going to be 6 stress components corresponding to the strains. Right? Now, that's very good. I just quickly list all the equations we need. Now, if you look at this is going to be very difficult to solve in most cases because our solids are usually quite complex in structures. And what we do use in reality most of the time is going to be numerical methods. But there are some analytical methods that we can use, right? For some simple problems we can solve. Now, right, let's go back to this a little bit for a moment. Now we have all the equations down, and obviously the boundary conditions. We need boundary conditions to solve. So what we mean by boundary conditions is, for a piece of solid, what is the external forces or displacement being imposed on the solid, right? So the boundary conditions are specified or only on the surface. So there's prescribed traction and prescribed displacement. That traction is another term for external force that we apply. Now, so you're going to see all these terms when we go into finite elements simulation. That's why I like to actually list all of them here, so you know what we mean. So the elasticity problem that we're going to have been solved in the past based on analytical methods most of the time in the past before we have numerical methods, and that is quite limited. But there are a few of these methods that you may have seen in mechanics of materials. This includes power series method, Fourier method, complex variable. Now the one that is most interesting to us is Airy stress function. So I hope you have seen this before as well. Airy stress function that we use quite a lot to solve two-dimensional problems, simple two-dimensional problems. So now beyond that, so when I say exact analytical method, so we are looking for mathematical functions that give the stress or strain distribution exactly. So there's no approximation, numerical approximation to it. It's going to be exactly correct. Now, it's very hard to find because this becomes a applied mathematical problem, solving the ordinary differential equations coming out from this three sets of equations. Now, there are also approximate analytical methods. The Ritz method, was the one of the early ones. Didn't go very far because the sort of approximation functions are very hard to find. Basically, in Ritz method, instead of finding a analytical function for the stress field, you approximate it by a summation of different functions, right? So then you can approximate any functions with that sort of subset of functions. But it's very hard to a priori choose what the stress or strain functions look like. So you can't go really far with that. But it gives a lot of insights for doing completely numerical methods, right? So the risk method is actually very instrumental for what we do in numerical methods. Now, so this is where I want to talk a bit more about. Now, numerical methods for solving elasticity problems. We use finite element method most of the time in solid mechanics. Right? There are other methods like finite difference method. So that is a little bit more. That is more common and popular in fluid mechanics. Right? You use finite difference method. So the difference between these two is how you discretize the set of equations. Right? In finite difference method, because you are dealing with differential equations, so you can directly numerically discretize the equations, right? That's finite difference method. But in finite element method, you don't discretize the equations. Instead, we're going to discretize the whole solid, and we're going to discretize a piece of solid into a subset of small cubes or small elements. And on each of these elements, we use approximating functions to approximate the strain field and stress field. Okay, so this is the difference between that finite difference and finite element, and we'll talk a bit more about finite element, and you're going to see a bit more about that in your homework. Now, that's where the name comes from. We're going to dissect the structure or material into a large number or collection of small elements. Now, in each of these small elements, we can approximate the strain field with simple functions, because we only require them to work as a good approximation in a small region, as opposed to we are looking for an analytical function that can describe the whole structure, the strain field in the whole structure. That's a entirely different, a lot more difficult thing to do, right? But if you want to describe the variation, we can do that with quadratic linear functions, simpler functions, right? And then we discretize the solid into many small pieces, and different sort of numerical values on the functions. So, and we're going to deal with in this course again two-dimensional problems. There are two main assumptions that we deal with in 2D problems, right? There's a plane stress problem and plane strain problems, right? Now, meaning that when we say two-dimensional problems, that means that we are assuming the stress or strain, either stress or strain, is not varying in one of the dimension. For example, in the thickness direction. So there's only stress distribution that is varying with, for example, x and y, but they don't vary with the z direction. Okay. So when we're dealing with, for example, very fat plates, a piece of, this small desk on the chair. This is a plane stress problem, right? We can approximate this as a plane stress problem because most of the stress, when you're going to, under the conditions that we load the material or load this, small piece of a desk, it's going to create stress that only varies in the plane of the solid. Okay, in the thickness direction, there's very little variation, so it's a good approximation. Now, plane strain is the other way around. Now, we have plane strain problems that usually works on very thick solid. Okay, so there's no strain in the third direction. So that's plane strain and plane stress. Now, most of the problems we're going to deal with belong to either of these, right? In the fracture mechanics problems in this class. So, I talk about quite a bit of this. So I just want to give you maybe a very quick guide to finite element analysis, actually using finite element analysis software. So there's an entire class on finite element method that I encourage you to take. It's very useful course that tells you about the theory and implementation. So I'm not going to do that, obviously. And this is just a guide to help you to do your homework, because when you go into the homework, there is going to be a finite element software that you're going to deal with, and there are some, just a few simple steps that allow you to kind of get an overview, and what it entails to solve a problem in an FEA. So now all the equations that I just wrote down for you, those equations are going to be taken care of in the finite element analysis. So you don't do that, right? It's all in the background. It's solved for you. So you only specify the things you want to analyze, right? So, and these are a few simple steps, right? You define the geometry of the solid, right? It can be a chair, it can be a car, it can be a building, it can be an aircraft. That's what I mean by the solid or the structure, right? You draw it out, the geometry. We're going to do again very simple problems with simple geometry, right? That's because we can compare our numerical solutions with some established analytical solutions. Okay, and so the second part, you create a mesh. That's what I just talked about, right? That's the mesh is just a name of a collection of elements, right? And if we think about an element in finite element language, for example, if you look at a cube, so you cut a big piece of block into smaller cubes. That cube has nodes because that cube has 8 points, right? The points are called nodes, and the volume that is enclosed by these nodes is the element. Okay, nodes and elements. Now then the total of this nodes and elements become the mesh, right? We call mesh. Now, what you need to give then is the material properties, because now that is what you want to analyze, right? You can be using a steel or other materials, right? So you got to define that. You got to tell the program what you're using, because it's going to give you only garbage if you give it garbage, right? So you define something so that it can calculate for you. Now, elastic properties for materials, you only define two. Modulus and Poisson's ratio, or you can define other two sets of constants. And the final steps. Now then you impose the forces that you want to apply. It can be displacement, it can be pressure forces, whatever, right? That is for you to define. And eventually you run the analysis, obviously. In Abacus, I don't know. I hope you have the chance to just install it and try to run it. So there are more. These are very simple, general steps in every finite element analysis. So each software may have its own technical details that it wants you to define things in a certain way, and they're not very fun to deal with, but they are necessary to be able to run an analysis. So I suggest you. They take some time for you to just figure out what they mean. So I suggest you to install that software, run a very simple analysis, just to be able to get through an analysis and you understand the whole process. So this is what we're going to do. In the first homework, I'm going to give out a simple problem related to fracture mechanics. Also, just for you to exercise that. Of using FEA. Now, I think there's one other thing I forgot to say about this. Right. So there's a caution about using finite element analysis. So it does all the work for you, and so your responsibility, or being an engineer. What you need to do is to be able to interpret the results, right? Because finite element analysis is a tool that gives you some numbers in the end of the day, and you can't trust it. Okay? You always have to think about whether your computing is correct, right? So the interpretation and the assessment of what the results coming out is the most important, right? Running the analysis is not everybody can run it after some practice. So but being an engineer and a mechanics person, what you need to do is to discern whether you're doing the analysis correctly, or why you're doing it incorrectly. If the results come out they don't make sense, right? So one way, how do we decide that? One way of doing it is to compare your model to a very simple analytical problem with established analytical solutions. Okay? Think about a beam bending problem. You can do a beam bending, you can calculate displacement very precisely analytically. That does not require numerical methods. So if you want to set up a beam bending, problem for a complex geometry, first of all, what you want to do is let's see if your process works for a simple beam. Check that against an analytical solution. If that works, then you go back to your final element and start, adding in more advanced geometry or maybe different material properties and so on. Okay, so it is critical that you check, the analysis. So again, I'm going to, put some more instructions in the homework just to make you, to push you through that process. Now, one more thing about final element, and then we are done. It's about mesh refinement. Okay. This is one of the problems that I've seen, many times in the past semester when I taught this course. Is that you have to, appreciate what we mean by meshing and mesh refinement when you go into doing this, because, for example, I'm showing you here 4 different meshes of different density, right? Same geometry, same solid, and they all give different results, right? So what you're seeing here, the color means the stress distribution, okay? Obviously, the one that here you can see is there are more elements, smaller elements around the hole. There is less, or larger elements around here, away from this feature. Compared to this one, this is really coarse. We call the mesh very coarse if the number of elements is small, or very little elements, and or other way saying this is the element size is large, right? And so which one is better? I mean, obviously the answer is this one, okay? So small elements always give you better or more precise answer, right? In elasticity problem. So you want to go as small as possible. Obviously there is a cost to it because your computational costs go up. So you don't want to overdo it, right? Or all the smart engineers, they do this sort of meshing so that you get the most accurate answer at the position where you're most interested in, right? So that's where the hole is, because there's the concentrations around it. So you want to be more precise over there, but you care less about the area outside. And so you form a non-uniform mesh where, the mesh is, dense around here and not so dense around. So you kind of get a trade-off. So this is what a final element practitioner routinely do to balance the computational requirement with accuracy. So I brought this up because the student version of Abacus is limited to 1,000 elements. Okay, so it's free, but there is a limitation. You can't solve real problems really with 1,000 elements. It's too small. But we still can, by adjusting, right, for learning purposes, that still works, right? But then I want to point you to this because this is something that you may find useful. I have, students before that they never get a good, for example, fracture stress intensity factor because their mesh is something like this, right? But if you're limited by 1,000 elements, you need to do something smarter, right? You lose some of the mesh density around here, and then you focus on here, right? That will improve your solution. Right, so that's mesh refinement, just one practical thing I want to talk to you. Now, let's go back to the topic we want to talk about, which is the floor size, okay? So remember back in the days that there is no final element simulation, and all we do is trying to use analytical solutions, and that actually gave us, very pretty insightful solution already. Now, so how do we take into account the presence of flaw in the calculation of strength? Well, one way to do this is to solve for the stress field with a hole that we will consider that as the crack or the flaw, right? So imagine here we consider an infinite plate, right? All this solution is produced by Inglis in 1913. Okay, this is a very early solution, one of the early solution of elasticity problems. Very practical, right? It's used in many areas at that point. Now, we model the crack or the flaw by an elliptical hole, right? We have a plate that has one elliptical hole, and we apply uniaxial tension, right? This is just like what we're doing in the lab. We take a piece of material and stretch it, but at that time we didn't know there's a crack. So, right? And now what we want to do is to solve exactly for the stress around the flaw and finding the stress field around that piece of solid. Now, we have an elliptical fall, and that is going to be described by, the major axis 2a, and then, the width is 2b, right? And, by intuition, and maybe you have also seen this in elasticity, is there's a stress concentration, right? And the stress concentration is going to be around which point? Under this stress, applied stress, we're going to see the maximum stress around point A, right? Just right at the tip of that elliptical hole, right? So this is where we expect the stress concentration to be appearing, right? So I'm going to show you the solution obtained by Inglis. What is the stress, maximum stress at that position? Okay. So we're going to do a finite element simulation on this problem. So you have a better visualization of the actual stress field. Now the mathematics of solving this analytically is quite painful, right? So I don't want to show you that because there's a lot of derivation and mathematics. So I want to just show you the final result and talk about the physical insights from that solution. Okay. So we have an infinite plate. An elliptical hole 2A and 2B. Now, the maximum stress is going to be here, right, at the tip, or here or there, right? It's the same. It's a symmetric problem. Now, at that point, we call it point A. So the solution by Inglis, that is in 1913. It's surprisingly simple. Okay. So you have the applied stress sigma, and the stress is going to be concentrated around A, is going to be intensified around the flaw, and by how much? Right? We know about stress concentrations by this time, right? All along, we just have no way of calculating it. So Inglis calculated it theoretically by solving the elasticity problem. Right. So if we remember solid mechanics, we talk about stress concentration factor, which is just sigma A over A. Sigma A over sigma. Now, so take a look at this solution, right? We see that the maximum stress we see is going to be increasing with the length of the flow, right? right? That length of the floor is characterized by 2a, and we know that if we, for the same amount of applied stress, a longer crack or a longer floor is going to give me a higher maximum stress around here, right? So I mean that's just a physical thing. Now, but what we can get is to extract more insight from this, right? This is a solution that we get. So English go into a bit more detail, right? But what we really want to understand is to make this crack extremely sharp, right? Because the floor is going to be small compared to the body, typically, and so he's going to take. Why don't we take find the stress at the crack tip as we push this crack to be extremely sharp, right? But how do we do that analytically? So one way to do this is to express the curvature of the ellipse at the tip, right? Because we know that if the curvature of the radius of curvature goes to 0, that means we are approaching a very sharp crack. Okay, so the first task is to find analytically the curvature at the crack tip. So this is an ellipse. So we're going to find the radius of curvature at the tip of the floor. Now we know the geometry of that ellipse, and we know the equation of an ellipse, and we can parameterize it. And if you go back to calculus, the x and y coordinate, assuming that we have this origin here, you can parameterize the ellipse by the polar coordinates, right? Theta and a and b are the major and minor axis of the ellipse, right? So this is just simple ellipse equation. And if you refresh your memory on the perhaps calculus 2 or calculus 3, when you differentiate a curve, you can find its curvature. But now you have the x and y coordinate of that equation. You can express the curvature by the derivatives. So this is just from calculus, right? So one prime is the first derivative. Double prime is the second derivative, right? So this is the parameterized equation of an ellipse, and the curvature obviously changes as you go around the ellipse, and it's expressed by this, right, analytically, right? Just differential geometry. Now, but with these we can actually calculate exactly what this curvature is, and then once we do that, we will express the curvature right at the tip. Okay, so what we need to do is just to do the differentiation, and these are all very simple derivatives. So in the end, you get this result for the curvature of the ellipse. So, carrying through the calculation, get AB Okay. Now that curvature equation works for the whole ellipse. Now, but what we are interested in is at the tip, right? Exactly, we are interested in the tip, the curvature at this tip, right? So at this tip, theta is 0, yes? Theta goes from here, 0, and go counterclockwise, right, in polar coordinates. Now, theta is going to be 0, and therefore, the curvature at the tip is just taking theta to 0, then we get this term to go to 0. And it turns out to be quite simple. The curvature of the tip is just a over b squared. Now this is the curvature. We like sometimes to look at the radius of curvature, which is just 1 over kappa. Now this is the radius of curvature. This is the curvature. So geometrically, the sharper the crack, that means curvature is higher, right? The curve has to bend around in a smaller distance. But conversely, that means the radius of curvature is smaller, right? Higher curvature, smaller radius of curvature. That's very good. Now, remember what is the goal of English, right? We want to attempt to characterize that stress sigma A at the tip when this ellipse becomes a very sharp crack or sharp flaw, right? Because once we do that, then we can, take a look at this stress and see if we can relate it to the cohesive stress or the cohesive strain calculated from atomistic calculation, right? And that will set us to see if we can improve that calculation, right? So what we need to do is then to combine this result, the curvature, with the stress obtained at the tip. So what we need to do is then just do some calculation that will give us very quickly. So because we already have rho b squared over a, we have sigma a. Oops. So just combining these two, I want to express now sigma a in terms of the radius of curvature and the crack length a, right? So that's quite simple because we can do this. Sigma 1 plus 2 a squared b squared and just substituting that result here. So this is the first important result from English analysis. Let me box that. So in the case of elliptical hole, we have A and B, right? But there's only an elliptical hole. if we have a sharp flaw, that means that A is going to increase, right, monotonically, and then we want B to shrink, as the ellipse approach an actual crack or actual flaw, right? So this is telling us what it really is happening, right? Because the radius of curvature is the radius of curvature of the flaw at the tip, and A is the length of the crack, right? Now, so what this result tells us, there are two things it tells us. It depends on the stress, the concentrated stress at the tip depends on two things, right? Exactly, it depends on the square root of the crack length, right? So square root A. So it increases with the square root of the crack length. That's the first important result, and it has to be proven to be correct, right? So increase the length is going to increase the stress, and quantitatively it goes with the square root of A, right? The square root of the root of the length. Now the other implication from this is the radius of curvature. Again, if we increase the sharpness, that means radius of curvature goes smaller or larger. Physically, if the crack goes sharper, that means at the tip, the radius of curvature goes smaller. Yes, right. So as rho goes smaller, sigma A is going to go increase, right? So, but then exactly by in what way it depends on radius of curvature. Again, square root. Okay, so this is the contribution, because now we can conceptually tell you about how the sharpness increases the stress, but it tells you quantitatively exactly how it depends on it, right? So it depends on the sharpness, depends on the crack length, right? Now these are the two major result from this, physical insights from this. Now this, we can take this further, right? Because we want to understand what is the critical stress that correspond. We want to see if using this result will get us a better calculation of to resolve the discrepancy we see in experimentally measured strength and the theoretical strength calculated from atomistic calculation, right? Now, but there are some difficulties with this again, because if we want if we want a very, very sharp crack, that means we are going to allow the radius of curvature, rho, to go to 0, right? So if as rho tends to 0, the crack becomes extremely sharp, atomically sharp. But then this result tells us that the stress concentrated at the tip is going to become infinite. Okay, right? Rho goes to 0. Every term is small. This term goes, it's going to explode. That means that sigma A is going to go to infinity. And that is not good, because we can't accept infinity in our calculation, because physically that doesn't happen. Now, this is, an insightful result, but then still a little bit of controversy. There's a lot of, more questions that generated here, right? So, but part of this result is still holds, right? So the sigma square root of A dependence of the crack length, that is true. We still prove it to be true later on. But we want to bypass that, atomically sharp crack. As the rho goes to 0, the stress goes to infinity. We want to, be able to bypass that, this inaccuracy in the solution. And so there are later on, we're going to introduce you a different approach to circumvent this difficulty. But one of the reasons that this is not working, right, is that we have been using a linear elastic solution, right? English uses a linear elastic solution and it assumes this is to be. He assumes it to be correct all the way up to the point of fracture. Okay, and that is the main limitation or the reason for this infinite stress prediction, but at the crack tip we know that the stress is so high, and that linear elastic solution no longer works, right? Because linear elasticity is based on continuum mechanics, right? So as rho goes to zero, you go to the atomic dimension, and that's not where linear elastic solution will work anymore. So we know there are some issues with this, but nonetheless, let's take this a step further and see what can we improve at least the result from the classical string theory. Okay, so let me write down again the result here. So remember the classical string theory predicts the following. This is what we talked about last time. We have I think I used sigma c. I think so, right? Right? So this is what classical string theory assumes, because we know the cohesive stress calculated from atomic calculation is related to the elastic modulus, the equilibrium distance, and the surface energy. This is what we calculated last time. And classical string theory says that, well, it has to be the same. The applied stress, once it reaches that, is going to fail, right? So now English improved that, right? Because now it's not sigma that is important, it's sigma A, right? So instead of sigma, I'm going to set sigma A equal to sigma C and sigma A is just going to be what we just derived, or what English have derived. Now I'm going to make a approximation to this equation, because that's going to make the math a bit easier. Okay, so what I'm going to do is I'm looking at this equation and see that, well, A is the length of the crack, right? So if we think about ceramics, for example, the crack or the flaw size is on the order of microns, right? So A typical order of microns, right? 10 to the minus 6 meter. And if we look at the radius of curvature, and if we say that this crack is atomically sharp, then the radius of curvature is on the dimension of atomic spacing. So, and that's in the order of angstrom. It's 10 to the minus 10. So an atomically sharp crack with the length of a typical flaw in a linear elastic material, right? So if you take a look at this A over rho, this is going to be about 1,000, right? No, actually, no, 10,000, right? And I can approximate instead of carrying the 1 here, because this term is going to be much larger than this, right? So we have taking the square root of this is about 100. So this is 200. Yeah. So if I omit the 1, that's going to be okay, because that gives me only about 0.5% error. So I'm going to omit it just to make the math easier. So I'm going to approximate. Let me write here. Sigma is approximated by sigma A over rho. Okay. So the argument is just what I said, because we want to omit this one based on the fact that this dimension is very large. Okay, so that gives us a better or easier expression. Okay, let's keep going, because I want to find out what is sigma. So if you just manipulate or get around the algebra, but this is just simply E gamma over A, and we have rho okay. So let's take one more assumption, right? Because we are looking at atomically sharp crack. So rho, radius of curvature at the tip of the crack, is similar to x0, because x0 is the atomic dimension, right? The equilibrium distances. So we can eventually get to an improved version of the string theory. Oops. So remember, right, classical string theory says that, well, we're going to measure sigma, right? That's the one that we can measure, because sigma is the stress that's being applied, right? That's all you can measure in an experiment. We're not measuring sigma A, we are not measuring sigma C, we are measuring sigma, okay? Now, sigma is what you measure, and it says that, well, sigma has to be E atomic, the theoretical strength, which is E gamma of x0, right? And we know that from last lecture, these two don't match, because this one is a lot larger than that one. Now, let's say that, now let's come to English, which we now know. It does not depend on the atomic dimension anymore, right? Instead, there is one more dependence, which is on the crack length. So this is, again, what we can measure. But instead of taking the atomic dimension of the solid, you have to go to measure the floor size of the sample. You still need the surface energy of the material. But instead of the atomic dimension, this is replaced by the crack length, A. So now let's examine, does this make sense, right? So as the length goes, as the length increases, right, as the floor size increases, what happens to the strength? It's smaller, right? A larger crack means that you're going to measure a smaller strength, right? So this actually, in the end, gives it a much closer expression than this one, right? Because the length here, if you just compare these two, you're going to see that the dimension exactly scales with what is the floor size, right? Because over here, what you get is going to be in the order of angstrom, right? And it's really depending on the material. It doesn't matter on how many cracks in there, right? You get the chemical composition of the material, and then this one is set. But here is not. You get the same material, but if there are more cracks in this one than the other one, they're going to be different strengths. And that strength, that A is typically, for ceramics on the order of, microns, which is, several orders of magnitude larger than what you're going to put in here. So this is a lot closer to what you get to measure in reality. Now, but still, this is not extremely useful. So English, this is a good approximation, but theoretically, this is still a very difficulty because that it predicts a stress that's infinite at the tip. So as mechanicians, we can't accept that, right? Something theoretical is wrong with that. So even though it's a very good idea, still this is not being used until the work of Griffith. Okay, and so. How much time do I have? Okay, yeah, at least I can make an introduction. So, that issue was tackled and by Griffith. Okay. So he wanted to solve the same problem, but he didn't want to. He wanted to avoid the issue at the crack tip, which is infinite, right? So he was thinking a different way approach to find the conditions of that determines whether a crack will grow or a certain material will fracture based on energy, right? Instead of looking at the stress, he wants to use an energy balance and approach, and this is what we're going to start, and we'll keep talking about this also on the next lecture. Okay. So let's take a look at this. Right? It's a very simple. It's very similar problem that English is trying to solve. Right? Basically, he read English solution, and he thought of a different idea of approaching it. Right? In the end of the day, what we want to understand is at what conditions is a crack going to get larger, right? Because there are already pre-existing flaws in the material, so there are already some cracks to begin with. And when we talk about fracture, that means that the flaws get larger. It increases in length, right? And eventually it increases so much that it breaks the material into big pieces. So the starting point is, okay, there are some cracks, and what are the conditions, in terms of stresses, and also the pre-existing crack length that will allow the crack to grow, right? That is the question that he wants to solve. Now, and he used the energy balance equation, and now we are looking. Let's consider this a very similar-ish problem that English have solved. Now, because the reason for that is because so that he can use some of the results that English derived. Now, again, we are looking at a pre-existing a plate. Now, there's a pre-existing crack in there, right? Everything is similar, right? We have an elliptical crack, 2A in length. Now, there's certain thickness to it, thickness B. Some stress is being applied onto it, uniaxial tension stress, sigma. Now, but then we're going to do a comparison of the energy of that piece of solid before and after a crack, before and after crack growth. Okay, so because from thermodynamics, we know that if the what determines whether a process will proceed is whether the energy after the process is lower. Okay, so this is just thermodynamics. Result from thermodynamics that all the physical systems try to minimize free energy, right? So there's an existing flaw, and there is a flaw, a piece of material with an existing flaw, and same piece of material with a slightly larger flaw, right? So if it has to grow, that means that the configuration with the larger flaw must have a lower energy. Okay, so if that is the case, that means that crack will grow. If not, it won't, right? So if the length increases but the whole system gain in energy, then it's not going to happen. It's not permitted by thermodynamics. So then the logic becomes quite simple, right? Well, let's calculate the energy of the system before the crack advances and after it advances, right? So and then you see by comparing the energies of these two, we can derive the condition for when this crack growth happens. So this is the thought. This is the basically the whole train of thought. Now, what we need to do then is to calculate all these energies. Okay, so. So assume you're familiar with string energy. Yes? String energy density. Have you heard about it? Yes? So you know how to calculate. So I'm not going to go through that. So I'm having two copies of the plate. So just do this thought experiment. Some stress is being applied. Another copy of the same piece of solid. So the width is B. But this one has a crack of 2A. So imagine this situation. I have a piece of material, there's no crack. I load it to sigma, and then I fix the loading grips. Right? Once I reach sigma, I stop there. So I have two loading grips. I stretch to, once I reach sigma, I stop. Right? So the displacement of the plate is being fixed. Right? Now, same thing here. I load it. This is two different specimens, by the way, right? Two different specimens. This one I make a crack inside, 2A. I measure it, I make a crack, and then I drill a hole, I make it crack here. So I know exactly it's 2A. And I load it with the loading grips to sigma, and I stop there, right? I don't move anymore. Okay. So the first thing that so we have to account all the difference in the energies. Okay, they're all energies that are different in these two configurations. Right. The first one is what we talked about before, which is the surface energy. Okay. So think about these two configurations. This one has two more surfaces than this one. Yep. Because we pull out a hole here, and there's the surface energy. And so there's a difference in the surface energy. And if we take gamma is the surface energy density, right? That is the it measures in terms of energy per unit area. So it's going to be energy per unit area. Or you can say this is, Newton meter per meter. All sort of different units. This is the surface energy density, right? So it measures an energy per area, right? So we just have to count how much area we have here in addition to this configuration. Now we have two surfaces, right, top and bottom. So there's a 2. So that the surface is length of 2a, and the surface has a width of b. Right, that's the total surface added in this configuration. And just take that total surface multiplied by the surface energy density. So this is the difference in the surface energy between these two configurations. Okay. Now there's also an external work difference. Now the external work difference is exactly 0. Okay? That's just because we applied, we have the two loading grips. We applied to a force of sigma, and we stop there. So in between these two, if I go from this configuration to this configuration, there's not going to be any more external work done. Even though there's a stress, there's no work done because I stopped the grips. The grips, there's a stress, but work done is the stress multiplied by the length, the displacement that stress go, right? So in between these two, there's no difference because the grips have stopped. We make it stopped, right? We don't want any work done. So the last thing is that we need to count for the string energy difference between these two. Now this is where it becomes difficult because now you need to calculate the stress field and use that stress field to calculate the energy. And again, there's a lot of mathematics that goes behind it that I'm going to go through. So Griffith used the solution of English of the stress field, except not at the tip. But he integrate the stress field and the strain field around the whole body. And then he calculated a quantity for the energy, elastic energy inside that body. And so I'm going to show you the result right away. And this is what Griffith calculated. Okay, this is due to Griffith. That is the one that is, in the seminal paper he produced. This is one of the main results. Now, we're going to talk more about this next lecture, but just to point out, it's negative. That's because we use negative because we are comparing this one which correspond to this one. So this one actually has less elastic energy than this one. Okay, less elastic string energy in this one than in this one. And you can see why actually, because you have a hole here, and around that hole, around the material around this flow actually is not taking stress. They're going to take less stress, so the energy is going to be smaller. Now, but we're going to talk more about this in the next lecture. But this is the main result. We know that the elastic energy is going to decrease as the crack increases. And we have the surface energy that is going to increase. From here to here, we have a gain in the surface energy, but a reduction in the elastic energy. So we're going to do an energy balance next time and see what it gets to tell us. Okay? So I'll see you next lecture.